Welcome to online lecture 3 of unit number 2, thermal design of refrigeration system components on sizing of reciprocating compressor. So today's lecture we will learn or we will discuss how to decide the dimensions of cylinder of reciprocating compressor. This is the schematic layout of the reciprocating compressor. It's similar to our reciprocating air compressor. So it's a piston cylinder assembly with suction and discharge manifold, control volume, cylinder, piston. So the distance traveled by the piston from TDC to BDC, it is called as a stroke, and this is called as a bore, connecting rod, crankshaft. So the principal dimensions of reciprocating compressors are the bore D and stroke L, and these are to be decided in conjunction with the RPM. So that is rotational speed of crankshaft, or the mean piston velocity, because this is connected to the piston through connecting rod. So either RPM or the mean piston speed, so which is given by twice L n by 60. So in one particular revolution, so the piston travels the distance twice. So this is L and again 2L. So 2L into n by 60. So this is cm is the piston speed, that is in meter per second. Thus, overall, there are three parameters: diameter, length, either speed, piston speed, or RPM to be selected. So these are the parameters to be selected while designing. Stroke to bore ratio, that is equal to L by D, is a very important consideration in compressor design. So only one equation is associated with the design of refrigerant compressor. So that is the equation related with the suction volume, because that is directly connected with the mass flow rate. So suction volume, which is given by mass flow rate. So this particular term is called as mass flow rate. That is refrigerating capacity divided by refrigerating effect into specific volume. So mass flow rate into specific volume, that is equal to a suction volume. So that is actual volume inhaled. So this is one expression we have, that is to calculate the suction volume, which is related to the dimension. And the another equation we have, that is in terms of volumetry, because as per the definition of volumetric efficiency, it is the ratio of volume inhaled, that is actual volume, upon theoretical volume. So V dot P is the theoretical piston displacement, and V dot S is the actual piston displacement, that we can say. So V dot P, we can say this is theoretical piston displacement, which is given by pi by 4 d square ln by 60. So that is for one cylinder. If it is multi-cylinder, then V dot S is double. So these are the constant. Pi by 4 by 60 is a constant, so it remains. So these are the variable d square ln. So piston displacement is mainly depends on these three parameters. So that is diameter, length, and RPM in meter cube hour. So if we put this equation in V dot S actual, so again it becomes, and instead of L we can put L by D, so LD instead of theta into L, theta into D, so D cube into L into volumetric efficiency. Sorry, if we put this equation, so if we put V dot P and putting L is equal to theta into D, and in this equation, suppose in this equation, the equation becomes V dot S, that is equal to 47.1 D cube theta and theta V, that is volumetric efficiency. Or in other words, instead of N we can put N we can write in terms of cm, so that is 30 cm. Well, N by 60, that is 30 cm, and L it 1D get cancelled. So this is another expression we have. So from this we can write the expression of diameter, that is a bore of the cylinder, which is given by this expression. So it mainly depends on the three variables. So now out of three variables, V dot S is generally given by the design specifications, because as per the design consideration, what is the suction volume required. So assumptions therefore necessary for two parameters. So two parameters in the we require assumption in order to calculate diameter. Now to minimize the friction and wear, the mean piston speed should be selected. So piston speed we can select. So in the range of 1.5 to 5 meter per second. So this value we have to select depending upon the conditions, and it should lie between 1.5 to 5 meter per second in order to wear friction and or in order to minimize friction and wear. At the same time, L by D ratio is also important. It's chosen based on the delivery pressure PD, because L by D ratio, if we see the formula of piston force is given by the area, cross-sectional area into pressure, delivery pressure. So larger L by D ratio is generally preferred for higher discharge pressure because it gives you smaller diameter and vice versa. So depends on the delivery pressure and the cylinder diameter to minimize the piston force and hence the inertia. So if we minimize the piston force, obviously the power required for the compressor also reduces. So large L by D ratio is chosen in high pressure compressors so that the diameter is smaller, and the following values are normally adopted in practice. So L by D ratio and CM, these are the values generally assumed based on the design conditions, based on the temperature limits. So these are some typical values of L by D ratio. For vacuum pumps or high-speed air compressor, L by D ratio is generally, so larger diameters are used, because for high-speed compressors are generally the discharge pressure is low, so smaller L by D ratio is used. Fluorocarbon compressors, it is near about 0.8. Ammonia compressor is close to 1. And high pressure compressors like 410A, the L by D ratio is very large, 4.6, to minimize the this thing. But make sure that some ANSYS analysis is required for this L by D ratio. Various research papers are also available because there is a possibility of buckling of the shaft if length is almost 5 times that of diameter. So the care to be taken. So there, before implementing the high L by D ratio, it is necessary to analyze that dimensions or analyze the piston cylinder assembly for various speeds and make sure that there should not be any buckling happens. So these are the dimensions. Now we will take one numerical part on this. So an R22 hermetic reciprocating compressor with a 4% clearance volume is given. Is to be designed for 7.5 TR capacity at 4 degrees Celsius. The corresponding pressure is also given, that is 5.657 bar. Evaporating. So evaporating temperature is 4 degrees Celsius. And condensing temperature is given 40 degrees Celsius with condensing pressure 15.335 bar. The compression index may be taken as 1.15. So compression process is not isentropic one, it is a polytropic one. So that process is given. The number of cylinders may be selected as 2. So it is 2-cylinder reciprocating compressor. And the mean piston speed, now it is assumed that mean piston speed is 3 meter per second approximately. L by D ratio is given. The stroke to bore ratio for fluorocarbons may be taken as 0.8. So L by D ratio is given. The pressure drops at suction and discharge valves may be assumed as 0.2 and 0.4 bar respectively. So there is a drop in pressure at suction as well as at discharge due to wire drawing effect. You will learn in actual vapor compression cycle in TE that how the pressure drops happens in suction as well as delivery line. Then the specific volume of suction vapor is given. That is the specific volume at the inlet of the compressor that is generally required to calculate the mass flow rate. And we have to determine the power consumption of the compressor, COP of the cycle, volumetric efficiency, and bore and stroke of the compressor. Motor speed is given in this case at 1400 RPM. So enthalpy at the inlet of the compressor is given, and enthalpy at the condenser outlet is given, that is H3, that is equal to H4. So by using these design conditions, we have to design a bore or stroke or design a compressor. So first of all, we'll calculate, because there is a drop in pressure. So the actual suction pressure is less by 0.2. So that is by evaporating pressure is 5.657. So actual pressure is reduced by 0.2. So it is around 5.457 bar, and the discharge pressure is slightly higher because there is a drop in discharge pressure. So slightly higher discharge pressure because condensing pressure is less, so it discharges at slightly higher because it should discharge at higher pressure than the condensing pressure. Otherwise, the reverse flow can take place. So in this case, there is addition. In this case, there is a reduction. So these are the suction and discharge pressure. If pressure drops not given, we can directly take this suction and discharge pressures as it is, PS and PD. It's called same compressor and delivery pressures. Now in this case, the compressor suction pressure and compressor delivery pressures are different than evaporating pressure and condensing pressure. Now first of all, we'll calculate the specific work as per the thermodynamic equation. Specific work of polytropic process, work for polytropic compression process, that is n upon n minus 1 P1 V1 into P2 by P1 raised to n minus 1 minus raised to n minus 1. So we have the values of compression index, that is 1.15 is there. Pressure at suction is given, that is 5.457. Specific volume at inlet is given, that is 0.0431, and pressures, that is P2, and this is called P2, or we can say PD and PS. So both all values are given, so we can calculate the specific work. So specific work is around 26.6 kilojoule per kg. So we have to calculate power. So multiply this by mass flow rate, we can calculate the power. But in order to calculate mass flow rate, we need to calculate refeeding effect first, because generally mass flow rate is calculated by using only two expressions, either with the help of cylinder dimensions or with the help of refeeding effect, not with the help of work. So cooling capacity is given. So first of all, we'll calculate the refeeding effect, that is H1 minus H4, both values are given. So that comes out to be 157.7. Then mass flow rate, that is cooling capacity, that is it is given 7.5, and refeeding effect, that is 157. So 7.5 is TR multiplied by 3.517 divided by refeeding effect. That gives you mass flow rate in kg per second. So with the help of mass flow rate, we can calculate power. So power is given by mass flow rate into specific work. It comes around 4.45. Then the COP we can calculate again by using specific work. So generally the octane values we can calculate, that is either with the help of cooling capacity, both expressions are the specific quantities we have taken here, COP. You can take actual quantities also. So actual quantities mean the rate quantities, we can say. That cooling capacity capital QL divided by work input, W dot. So that way also correct, because M dot get cancelled. So QL divided by, so this is QL, this is also QL. Don't get this. So QL divided by small w. Small w is 26 point. So the COP is COP is around 5.9. This is theoretical. So both values known to us. Now we have to calculate the volumetric efficiency. So volumetric efficiency, it is given by this expression, 1 plus C minus C into PD by P1 raised to 1 by N. So 1 by M is the compression index. The M is the N is the compression index. So the volumetric efficiency is around 0.8695. This is one of the, so green highlighted answers. These are the questions asked in the problem statement. So that's why we have considered. Now the cylinder dimensions we have to calculate. So piston displacement per cylinder. Now according to the expression of piston displacement, this is theoretical piston displacement, which is multiplied by volumetric efficiency into 2. So the total, that is because there are two cylinders, that is equal to m dot into small v1. So actual piston displacement, it is given by a mass flow rate into specific volume, which is equal to the theoretical piston displacement into specific volume. And as it is a two cylinder, that's why multiply by 2. So if we rearrange this equation, because we have to calculate theoretical piston displacement. So theoretical displacement, piston displacement comes around 0.252 meter cube per minute. Now, theoretical piston displacement is also given by this expression. That is, this is a theoretical piston displacement of one cylinder because already we have divided by 2. But while calculating the actual flow rate is the actual flow rate of the system. So system, there is a compressor, and compressor consists of 2 cylinders. So that's why while calculating actual specific or actual suction volume, the formula of actual suction volume is theoretical suction volume into specific volume into number of cylinders. Now in this case there are 2 number of cylinders, that's why we are multiplied by 2. So this is the theoretical piston displacement, that is pi by 4 d square into divided by 4 ln into, so instead of n ln we can substitute the cm, because instead of n we can put 30 cm, that that is in terms of mean piston speed, which is given. That's why in terms of this. So we have calculated the diameter. So with the help of, we can calculate, only unknown in this equation is diameter, because L by D ratio is given. So suppose if we rearrange this equation and if you put the values, because LL get cancelled. So only unknown in this equation is diameter. So diameter is obtained around 60 mm. So by using L by D ratio, we can calculate, as the L by D ratio is given as 0.8. We can calculate the length. But the speed is given, so we have to ensure with the help of the CM equation, we have to ensure what should be the speed comes. But speed comes around 1875 RPM. So, but actual case, the motor speed is given, so 1400. So we have to cross verify our answers. Now in this case, with the help of these dimensions, the speed comes higher than the given speed. So we have to alter the dimensions of L, D, and CM. So accordingly, as the motor speed is 1400, so with the help of motor speed, we can calculate first bore, stroke, and from stroke we can calculate the L by D ratio, because diameter we have considered as 60 as it is. This is ultra dimension, which is also high, very high, and it will result in, because this L by D ratio is high, with high L by D ratio causes increased frictional losses because length is more. So we have to reduce it. So we can average these two lengths. So instead of 64, 64 is high length. So because of this high stroke, there is a possibility of increase of frictional losses. So we take a golden mean. So that is averaging of this. So 64 or plus 48 by 2, that gives 56, and corresponding diameter also we average it. That is 64. So 64 is the diameter, and so we slightly corresponding from L by D ratio, we can calculate diameter. Then theta also we can modify, and piston speed is also slightly, because initially we assume piston speed. So all these 3 dimensions are altered based on the given information. So this lecture we have, so at the end of this particular lecture, you should be able to determine the principal dimensions of reciprocating compressors. So this numerical can be asked for 6 to 8 marks. It is again based on the reciprocating. So for that we have to, everybody is aware about the simple vapor compression cycle. So prerequisite for solving this problem, you must know the expression of polytropic compression process work. Then volumetric efficiency formula you need to memorize. Then how to implement, that is the main equation is used, that is the suction volume. So suction volume in terms of mass flow rate, or suction volume in terms of theoretical piston displacements. So these are the major equations used for analyzing or determine the size of the reciprocating compressor. Next lecture we will, now we have finished the compressor part. Now the next lecture we will see how to design the evaporators, the second important components of efficient system, that is evaporator. So designing of evaporator, that is especially DX and flooded type evaporator, that we will discuss in next lecture. Thank you very much.